Hello viewers, welcome to add-on. In this case, in this question we are asked, state the sampling theorem with its types and applications and discuss for a continuous time signal, determine the minimum sampling rate to avoid aliasing. Okay, now sampling, by sampling we are meaning, it is the process of converting a continuous time signal into a discrete time signal. Okay, now what is a continuous time signal? Suppose this is a sinusoidal signal, right? So for this particular waveform, for each and every single interval of time, the value is defined, right? Because at this particular point we are getting a value, at this particular point we are getting a value, and likewise for all the point on the time axis we are getting a particular value. Okay, but in discrete time signal, the signal is like this. Okay, so here in the discrete time signal we will be getting the value only at discrete time intervals, which is suppose this is 2, this is 3, this is 4. So we will be getting only the values at 2, 3, 4, likewise. Okay, so in the continuous time signal we will be getting the values at each and every interval of t, but in the discrete time signal we will be getting the values at only discrete time intervals. And now to convert this continuous time signal into discrete time signal, we will be following the process of sampling. Okay, so in order to convert this continuous time signal to discrete time signal, we need to follow sampling theorem. Now what does this sampling theorem states? Sampling theorem states that if any signal which is band limited to fm. What do you mean by the term band limited? Suppose this is a particular frequency band, right? For this particular signal, this is a particular frequency band. Suppose this is fm. So the sampling theorem states that any signal which is band limited to fm can be reconstructed from its samples. These individual lines that I am drawing here, these are the samples. So it says that any signal which is band limited to fm can be reconstructed from the samples if fs is greater than equal to 2 of fm. What is fm? Fm is the frequency of this continuous time signal and fs is the sampling rate. Okay, the fs is the frequency at which the signal is sampled. So let us see a visual expression of sampling. Suppose this is a sinusoidal signal. So when we do the sampling, what do we get? We will get like this. We will be getting some values at some discrete time intervals like this. Okay. So after sampling, we will get the signal like this, right? So I have drawn the outline of the sinusoidal signal in this case. If we remove the outline, we will get some signal like this. Okay, so if we connect the upper lines, we can see that this will form a sinusoidal signal. Okay, so this was a continuous time signal which was defined for every interval of t, and this is a discrete time signal which is only defined for some particular discrete interval of time. Okay, and the sampling theorem states that sampling rate, this is the rate at which the signal needs to be sampled, should be always greater than equal to twice of fm. Okay, so this is our sampling theorem. And one thing we need to know, this sampling rate, when it is equal to twice of fm, this can be equal to greater than twice of fm, and this can be less than twice of fm. So when sampling rate is equal to twice of fm, we can do the signal reconstruction. There is no problem in the reconstruction of the signal. When sampling rate is greater than twice of fm, we can also reconstruct the signal. But when sampling rate is less than twice of fm, we can't reconstruct the signal. Okay, this is one thing that we need to know, because fs is equal to 2fm, this is the critical sampling. Fs greater than 2fm, this is the oversampling. Fs less than 2fm, this is the undersampling. And what happens in the undersampling? Suppose this is a spectrum. Suppose this is a spectrum of the original signal. Okay, this is a spectrum of the signal which is obtained after sampling. This is the case of oversampling. Fs is greater than twice fm, we are getting multiple copies, right? But when fs is less than twice fm, what happens? The two spectrums, we can see, overlap each other. Okay, So when the signal, so in the case of fs greater than twice fm, when we reconstruct it, we will get a single spectrum or a single spectra like this. But in this case, if we reconstruct it, we will get a signal like this, which is not our desired case. Okay, so this is known as aliasing. Okay, so this problem arises when the sampling rate fs is less than twice of fm. Okay, so this is undersampling. This sampling can be used in various scenarios. One scenario that I've already discussed, to convert the continuous time signal into discrete time signal. It can be also used in digital signal processing in the signal processor. Sampling is also used in quantization. Quantization is the main process which is used in the conversion of analog signal to digital signal. So this is used for analog to digital conversion. And the types of sampling are ideal sampling, natural sampling, and flat top sampling. In this case, ideal sampling, we generally don't use ideal sampling. We only use natural sampling or flat top sampling. Okay, so let us now solve the problem which was given to us. The problem was 3 cos of 100 pi t. Okay, so this is the amplitude of the signal 3, and this is the angular frequency 100 pi. So 100 pi, this is the angular frequency. Okay, which is represented by omega. So we know omega is equal to 2 pi of f, which is equal to 100 pi. So if we cancel it, f will be equal to 50. Now we have asked determine the minimum sampling rate to avoid aliasing. Now we know sampling rate when it is less than twice of fm, aliasing occur. So in order to avoid aliasing, we need to make it greater than equal to twice of fm. What is twice of fm in our scenario? Fm is this particular frequency, which is the frequency of the original signal or the signal which is sampled. So here in this case, twice of fm will give us 2 into 50, 100 hertz. Okay, so in order to avoid aliasing, the sampling rate should be greater than equal to 100 hertz. Okay, if it is equal to 100 hertz, it will be critical sampling. If it is greater than 100 hertz, it will be oversampling. So by choosing the sampling rate according to this condition, we can easily avoid aliasing. Thank you.